Jupiter drifts through the cosmic dark like a colossal sentinel, glowing with a quiet, otherworldly majesty. From afar, it appears as a striped sphere. Its alternating bands of orange, beige, and white hint at something deeper. This is no ordinary planet. Jupiter is a gas giant so massive that it outweighs all the other planets in our solar system combined. But what fuels the energy beneath its swirling clouds? What drives the hypnotic stripes? And how does this giant remain in motion for eons? Today, we journey beyond a planet. We enter a living laboratory where gravity, chemistry, and atmospheric dynamics collide in breathtaking ways. Composed mostly of hydrogen and helium, the building blocks of stars, Jupiter came close to becoming a sun, yet never ignited. Instead, it holds onto a deep internal heat, a relic of its violent formation. This quiet radiation escapes through its thick cloud layers, telling stories of a chaotic birth. What causes this planet to remain so active, so radiant from within? And what invisible engines keep its atmosphere swirling in perpetual motion? As we draw nearer, Jupiter's faint halo of rings and distant moons, usually lost in its glare, come into view. Each a thread in the gas giant's vast and mysterious tapestry. What lies beneath those clouds? Where have the obvious surface features gone? And what strange, inexplicable forces hide at the planet's poles? As we explore, we're guided by stunning visuals from NASA's Juno spacecraft and animated sequences built from real scientific data. Up close, Jupiter's face is a turbulent work of art. Rich ochre bands, dark brown belts, and pearly white zones sweep across the globe in near-perfect symmetry. These atmospheric features are anything but static. They are the fingerprints of fierce winds that race around the planet at staggering speeds. Each of these bright and dark stripes is shaped by jet streams, east-west flows that circle the planet in alternating directions. These high-speed currents segment Jupiter's atmosphere into a series of zonal flows that stretch from the equator to the poles. In the lighter zones, clouds of frozen ammonia rise from the depths, reflecting sunlight and appearing pale gold or white. Meanwhile, the darker belts expose deeper atmospheric layers rich with compounds like ammonium hydrosulfide, giving them shades of copper and rust. Each adjacent band moves counter to its neighbor, creating a pattern of organized chaos. Jupiter's jet streams can exceed 400 mph, dwarfing anything seen in Earth's atmosphere. These relentless winds are sculpted by the Coriolis effect, a byproduct of the planet's rapid rotation. This spinning force breaks the atmosphere into dozens of high-speed jets, between which lie the planet's bright zones and dark belts. These belts are more than aesthetic. They're meteorological power zones that shape the weather on Jupiter in permanent, unpredictable ways. Deep inside the planet, leftover heat from its formation powers enormous convection currents. These rising plumes and sinking gases fuel the atmosphere from below, creating a feedback loop that keeps the winds alive. The result? A planet with jet streams so stable they remain fixed for years, even decades. Yet at the edges of these zones, we find turbulence, fine waves and eddies where wind shear creates rippling patterns. Here, ammonia and water vapor rise, condensing into high-altitude white clouds. In descending zones, the sky clears, exposing darker layers beneath. This interplay generates a marbled pattern that wraps around the planet like a weathered shell. And among these chaotic bands rages the most iconic storm in the solar system, the Great Red Spot. Towering high in the southern hemisphere, this salmon-colored oval has persisted for centuries, large enough to engulf our Earth with room to spare. It's an anticyclone, a high-pressure vortex spinning counterclockwise, rising above the surrounding clouds in a relentless spiral. When viewed up close, the Great Red Spot resembles a dense, swirling ring with a distinct reddish hue. Scientists suspect the color comes from complex organic molecules or phosphorus-rich compounds pulled from deep below. High above it floats a hazy dome, its exact makeup still a mystery. Inside the storm, bands and eddies twist like the iris of an enormous eye. Winds at its perimeter can exceed 268 mph, pulling surrounding cloud matter into its vortex. Occasionally, smaller storms crash into it. Some get absorbed, others deflected. More than just a storm, the Great Red Spot is a dominant feature in Jupiter's atmosphere, shaping weather far beyond its boundaries. While it has been shrinking over recent decades, it was once twice its current size. It still reigns as the largest and most powerful storm known to science. It rotates once every 6 Earth days, with a surprisingly calm center surrounded by violent, spinning jets. Lightning has occasionally been seen flashing within its massive structure, brief, haunting bursts that light up the haze from within. Measurements from the Juno spacecraft suggest that the storm doesn't plunge as deep as once thought, but still towers above the surrounding cloudscape. It's an inverted hurricane, spinning at its top, rooted in the planet's heat and winds. Over time, it may have merged with other long-lived vortices, evolving into the stable giant we observe today. But it's not alone. Jupiter's entire atmosphere teems with vortices, smaller white ovals, turbulent eddies, chaotic wind corridors. These anticyclones, similar to the Great Red Spot but smaller, can last from weeks to decades. In some latitudes, they align like pearls in a necklace, curving around the planet in elegant chains. Some of these storms combine. In 2000, 3 white ovals merged to create Oval BA, which later reddened and earned the nickname Red Spot Jr. Between these swirling giants, the atmosphere is filled with strange formations. Wind shear at jet stream boundaries creates long, wavy patterns. Kelvin-Helmholtz waves formed when layers of air slide past one another. Bright, popcorn-like clouds indicate rising storms. Tiny dark barges drift by, low-pressure spots in an ocean of turbulence. Since Jupiter lacks a solid surface to disrupt weather, storms can dive deep and last longer than anything on Earth. We also find countless miniature vortices, some just a few hundred miles wide, spinning across the belts. They often gather in turbulent zones near massive storms. One example, trailing the Great Red Spot, is a region filled with chaotic clouds and young vortices. This is a breeding ground for new weather systems. Yet, amid the chaos, a surprising order holds firm. Each storm remains anchored within its latitude band, corralled by powerful jet streams. While the equator and mid-latitudes look wild, Jupiter's poles reveal symmetry. From above, Juno found polar cyclones arranged in perfect geometric patterns. At the North Pole, 8 swirling cyclones encircle a central one, forming a stable octagon. Each storm spins counterclockwise, tightly packed, yet never merging. A strange balance keeps them in harmony. The South Pole presents a similar scene. Originally, 5 storms surrounded the center, with a 6th joining to form a hexagon. These polar clusters barely shift over time, locked in position by hidden forces. It's a breathtaking pattern, chaos ruled by symmetry, vortex physics dancing in place. Suddenly, a flash. Lightning crackles through the clouds. Jupiter's storms generate bolts more powerful than anything on Earth. First spotted by Voyager in 1979, these flashes originate deep within water clouds. But Juno discovered something more: shallow lightning. Here, in upper layers of the atmosphere, strange clouds of ammonia and water ice produce an alien kind of electricity. As hailstorms rage upward, they collide with falling icy slush called mushballs, a mix of water and ammonia. These collisions generate static, triggering lightning in regions colder than 126 degrees Celsius. These bolts light up the sky in blue and gold hues, illuminating towers of ammonia-rich clouds with ghostly brilliance. Some flashes last just milliseconds, but rival Earth's brightest strikes. Deeper down, where water vapor exists in all 3 states, ice, liquid, and gas, conventional thunderstorms rage. Lightning bolts here release energy far beyond Earth's most powerful storms. Juno recorded thousands of these bursts, hearing their eerie radio echoes, so-called whistlers. Interestingly, these discoveries also solved a mystery: Jupiter's missing ammonia. Mushballs were dragging it down from the upper layers, hiding it deep within. Now, let's rise beyond the storms. Above Jupiter's poles shimmer auroras, dancing ovals of radiant blue-violet light. They're the most powerful in the solar system, burning hundreds of times brighter than Earth's northern lights. Unlike Earth's auroras, which depend on solar storms, Jupiter's never stop. They're powered not just by the solar wind, but by the planet's titanic magnetic field, 16 to 54 times stronger than Earth's. This magnetosphere channels high-energy particles to the poles, slamming into the upper atmosphere. Hydrogen molecules are excited, releasing ultraviolet and infrared light. Some auroras even emit X-rays. Spiraling light displays form massive glowing rings, seen in ultraviolet but invisible to the human eye. Jupiter's magnetic field is driven by metallic hydrogen deep inside, rotating with the planet itself. Its moons also play a role. Volcanoes on Io spew sulfur and oxygen into space. These ions get trapped in Jupiter's magnetic field and whip toward the poles. The result? Bright spots in the aurora where Io's magnetic connection touches the planet. Similar auroral footprints come from Europa and Ganymede. These patterns pulse and flare when the solar wind intensifies. Finally, we pull back. Against the void of space, Jupiter wears a delicate crown, rings of dust. Unlike Saturn's brilliant arcs, Jupiter's rings are faint, thin, and ghostly. Discovered only in 1979, they shimmer like spider silk when backlit. The rings are formed by dust kicked up when meteoroids strike the tiny inner moons like Amalthea, Metis, and Adrastea. These moonlets continually replenish the ring with debris. These rings are nearly invisible, composed of microscopic rocky dust, just a few miles thick. In infrared or backlit images, they appear as faint glowing strands. They're held in place by the gravity of the planet and the orbits of the small moons, forming a quiet but vital part of Jupiter's complex system. Jupiter is not just a planet, it's a symphony of physics in motion. Its storms, rings, magnetism, and moons are all interconnected, driven by internal heat, rotational force, and the legacy of its formation. It is a world of extremes and balances, chaos and structure, violence and elegance. No matter how deeply we study it, Jupiter remains what it has always been. A majestic, eternal force in the cosmos, mysterious, powerful, and endlessly alive. If this journey through the wonders of Jupiter sparked your curiosity and left you wanting more, don't forget to subscribe to Space Future Now. Share this video with fellow explorers, and let us know your thoughts in the comments. What fascinated you most about Jupiter's storms, rings, or auroras? Your voice matters. Be part of the conversation as we continue uncovering the secrets of our universe.